Hello everyone, welcome to a new presentation about embedded control systems. In this presentation we are going to talk about robust control and its application to the servo of a hard disk drive. The death of the hard disk drive has been forecasted, arguing that solid-state drives will replace them. However, they are still around in most computers shipped today. In 2017, that is this year, according to Wikipedia, if you read Wikipedia, to get the same amount of bits per inch square in a solid-state drive as that in a hard disk drive, we need to pay 4 times more. In any case, I don't think hard disk drive will die anytime soon. The day when that happens, I will be very sad because the beauty of control systems won't be in the storage business. This is the first video in a series of videos where I'm going to illustrate the use of robust control to control hard disk drive servo systems. I would like to focus initially on track following, but if I feel inspired, I will do it for seek and spindle control. Let's start then. This presentation is organized as follows. First, we are going to review the theory of robust control. We start with a simple case of single input, single output systems, which can give us a good intuitive grasp. With this understanding, we move next to the case of multiple output, multiple input systems. Multiple input, multiple output systems. In this first video of this series, we are going to focus on the theory of robust control for single input, single output systems. In the next point, we deal with the theory of operation of hard disk drive servo systems. We will study the dynamical considerations of the track following, seeking, and spindle control. Major focus will be on track following. Knowing the theory of robust control and the plant we want to control, we set up our robust control problem. Then we designed our controller using MATLAB Robust Control Toolbox, which really eases the process of designing a robust controller. With the controller designed, we simulate our control system in Simulink as a MIL, model in the loop simulation. The goodness of our controller can be observed and modifications can be made. In our closure, we draw our main conclusions in this process of designing a robust controller for the hard disk drive servo system. Without further ado, let's start with the robust control theory. Here we have a typical control system based on feedback. The block diagram may be simple, but it's basic to understand the idea of robustness in a control system. Other more complex block diagrams can be simplified to this one. Here we have GS. GS is the plant. KS is the controller. The original idea of the controller K is to make sure the output Y follow the reference R. That is, to try to make E, the error, approach 0. But the controller has mortal enemies, and they are the disturbances DI, DO, and END. The disturbances are variables of which we have no control. They come and do as they please. DI is the input disturbance, DO is the output disturbance, and END is the measurement disturbance. The controller K must be able to reject these disturbances while allowing the plant to follow the reference. I haven't mentioned yet a very important limitation in all control systems. The knowledge of the plant, GS, is limited, and sometimes its mathematical model is an extreme simplification from a complex real physical system. Moreover, tear and wear change the plant's initial characteristics. We can say then that plant GS has variations from its nominal representation that can affect the performance of the control system considerably. In summary, when we design the controller with these goals in mind, good performance following the reference, able to reject the disturbances DI, DO, and N, and insensitive to the expected variation of the plant GS. We are designing a robust controller. From the block diagram, we can use block algebra to find Y and U, the two variables we need to watch closely. Initially, let's think that we are dealing with a multiple input, multiple output plant. Then GS and KS are transfer matrices, and all the variables in this diagram are vectors. In this case, knowing the multiplication order for matrices really matters, we get the following equations. This quantity over here is of great relevance, as we see next. That quantity is called the output sensitivity. We have also the complementary sensitivity, also known as the closed-loop transfer function. Between these two quantities, there is a relationship given by the following equation. This relation is important because it says that if we know one sensitivity, we know then the other one. If we are designing, for example, a controller to satisfy certain requirements for the output sensitivity, indirectly we are also fixing the closed-loop transfer function, and with that we are setting some performance features about the following of R, good or bad. We will talk more about this later. And finally, we have the input sensitivity given by this equation at the bottom. Once we got the equations for the multiple input, multiple output general case, let's consider the simpler case of single input, single output systems. This will help us to have a more intuitive grasp of robust control design. First, we should notice that we are dealing now with scalar transfer functions. In this case, output and input sensitivities are the same. And the closed-loop transfer function, which is also known as the complementary sensitivity, is given by this expression. The output Y then becomes, we are going to use this expression of Y in the following slides. In the equation of Y, we see that if we want to reject the output disturbance D0, we need to make the sensitivity small. Since we are dealing with complex numbers on the frequency domain, a more accurate statement should be, we need to make the magnitude of the sensitivity small. That is, the denominator of the sensitivity is called the return difference. The magnitude of the return difference must be big in order to reduce the sensitivity. The open loop transfer function is G times K. We can see clearly that the magnitude or the gain of the open loop transfer function must be large in order to reduce the sensitivity. Now, what do we need to do in order to reject the disturbance DI? We already know that the magnitude of the open loop transfer function must be big if we want to reject DO. With this condition, let's take a look at the product sensitivity times G. We see here that the magnitude of the controller has to be big to make the system insensitive to the disturbance DI. Notice that now both the magnitude of the open loop transfer function and the magnitude of the controller need to be large quantities. A large magnitude of the open loop transfer function is not enough to make the system insensitive to DI. Then the closed loop transfer function, that is the complementary sensitivity, becomes, and the output Y can be approximated to Notice that it seems we have succeeded making the system insensitive to the disturbances DO and DI, but we have failed miserably with the measurement noise N. Notice that the noise apparently goes through and affects the output completely. Well, not quite. We have forgotten that we are in the frequency domain and that what we have done is a comparative analysis of the frequency response magnitude, which varies in the frequency domain. Let's see this in the next slide. Let's summarize what we have obtained so far. To reject the disturbance at the output and to follow the reference, the magnitude of the sensitivity has to be close to 0, and the magnitude of the complementary sensitivity will be then very close to 1. We achieve that by making the magnitude of the open loop transfer function very large. To reject the disturbance at the input, we need to make the magnitude of the controller very large too. But if all of this is true, the measurement disturbance, that is, the noise NT, will pass through completely and won't be rejected. Moreover, if the magnitude of the controller is too big, this could induce big control signals that can't be handled by actuators. The control energy is always limited. What to do? In practice, we resolve this conflict because we know that some disturbances are more relevant at some frequencies than at others. For example, if R, DO, and DI are low frequency signals, as it's usually the case, we can make the sensitivity small at low frequencies and big at high frequencies. This way we can reject the high frequency components of the noise while we follow the reference R and reject the disturbances DI and DO at low frequencies. In general, we need to shape the controller K to provide the desired T and S. Let's illustrate this in the next slides. In this plot, we see the magnitude of the frequency response of a particular controller. We can say immediately that because the magnitude tends to infinite at low frequencies, this controller will reduce the effects of an input disturbance at low frequencies. And also because this controller has a high magnitude at the frequency W0, it will also attenuate an input vibration with frequency W0. In the mid-range frequency, the magnitude is low, and the system will be very sensitive to disturbances with those frequencies. If the plant has the typical low-pass filter frequency response, this controller will be also good to reject low-frequency output disturbances, but not necessarily it will be good to reject a vibration with frequency W0 at the output of the plant, unless we shape accordingly the frequency response of the open loop transfer function. In this other plot, we see the magnitude of an open loop transfer function. The range from 0 to W0 is a specified range in which the sensitivity has to be approximately bigger than 1 over epsilon, where epsilon is a small quantity. We want that because we want to reject output disturbances in this low frequency range. At higher frequencies, the system is very sensitive to output disturbances. In this plot, we see the magnitude of the sensitivity S and the magnitude of the closed-loop transfer function T. The frequency range between 0 and W0 is the range of frequencies in which we want the system to be very insensitive. The range of frequency from 0 to WB is called the bandwidth of the system. Reference signals with frequencies within the bandwidth can be tracked with ease by the control loop. However, there is a resonant peak for the sensitivity and another resonant peak for the closed-loop transfer function around WB. It's not difficult to see that if the sensitivity peak is too big, the system will be very sensitive to a disturbance with this resonant frequency. For performance reasons, this resonant peak should be small and the bandwidth WB must be big, so tracking the reference will be more accurate, with faster response. But the bigger the bandwidth, the more noise gets into the system because of the measurement noise. To reduce noise, we need to reduce the bandwidth, but if we do so, the response becomes slow and less accurate. This is the typical trade-off we need to live with. In all of this we have done so far, there is a caveat. We have been talking about magnitudes without the other aspect of a frequency response, the phase information. Without the phase information, what magnitude can tell us is not conclusive. Therefore, in all our previous analysis, we need to assume that the magnitude plots correspond to stable systems, so our conclusions are valid. To have an idea of the stability, we need to take a look at both phase and magnitude. Specifically, we can use the Nyquist criterion and the Nyquist plot to conclude about absolute and relative stability using the frequency response, magnitude and phase of the open loop transfer function. In this Nyquist, we assume that the open loop transfer function is a minimum phase system. By noticing that the Nyquist does not go around the point -1 J0, we conclude that the closed loop system is stable. By going around the point -1 J0, I mean this. In this case, in the case of the red Nyquist, the Nyquist stability criterion tells us that the closed loop system is unstable. And now let's go back at the original Nyquist. And by checking its phase margin and gain margin, we could conclude that the closed loop relative stability is very good. We need always to check both margins to determine the relative stability of the system. In my previous video, we found a PID controller for a hair dryer that allowed a good phase margin but a bad gain margin, something like this. The new red Nyquist has a very good phase margin but a very bad gain margin. The only conclusion we can draw from this is that the relative stability of the closed loop system is very bad. In reality, we want this Nyquist not only not to go around the point -1 plus J0, but also not to go too close to any vicinity of the point -1 plus J0. And for that, we could add another stability margin. In the plot is called SM, the inverse of the magnitude of the sensitivity, also called the magnitude of the return difference. Requirements for robust stability may be then A. The Nyquist of the open loop transfer function must not go around the point -1 J0. This guarantees absolute stability. And B. The magnitude of the return difference cannot be smaller than a predetermined value. We can see an illustration of this in the next slide. In this plot, the red vector is the return difference and the green vector is the frequency response of the open loop transfer function. The magnitude of the return difference is the radius of the circle shown. We can see that the bigger the radius, the farther from the point -1 plus J0, the better the relative stability and the more robust the system is. Notice that the system becomes more sluggish in its response as it becomes more robust. Observe that the minimum return difference occurs when the Nyquist is tangent to the corresponding circle. This corresponds to the maximum sensitivity, the resonant peak of the sensitivity we talked about before. In other words, to satisfy robustness, we need to minimize the peak of the sensitivity, or at least make it smaller than a predetermined value that guarantees an acceptable robustness. Let's remember this when we deal with robust control for multiple input, multiple output systems. So far we have talked about making our control system robust to reject disturbances, but we haven't yet talked about plant variations. In this case, we have a nominal plant G that is uncertain. Assume that the control system is perturbed by a variation of the plant G. We would like to know how the output is affected by this plant variation. The easiest way to approach this is to take the closed-loop transfer function T and differentiate it with respect to G. We obtain the following equation, which shows how the percent variation of T is affected by a percent variation of G. Plant variation can be considered as disturbances and can be mitigated again by making the magnitude of the sensitivity very small. Now we are ready to take a look at multivariable systems in the next video. Thank you for watching this video. Please subscribe. More information below in the description of this video.